Greetings and welcome, friends. Today we're going to take a different look at vectors, the same concept, just with a different approach. Instead of geometrically speaking, we're going to algebraically analyze them. So for starters, I've got this little representation of a vector as an ordered pair. So if I've got 2 points and I want to talk about the vector that starts at point 1 and ends at point 2, right? Because the direction matters, right? So vector P2, P1 is different than vector P1, P2, for instance. All I'd have to do is write it as this cool little ordered pair where I've got these awesome like angled brackets. They're so cool. I don't know. What's that? Is that maybe like a 160-degree angle maybe right there? Who knows? But anyways, what you do is you take your x2 and you subtract your x1. And that's your x coordinate in this little ordered pair that we have going on here. And you take your y2 and you subtract your y1, and that's your y coordinate in the little ordered pair. And now I can represent any vector in this format. Now, this ordered pair assumes that the vector is starting at the origin when you do it this way. So if you see a vector represented like this, assume it starts at the origin and then goes to the point of those particular coordinates. And then it talks about the magnitude of a vector, and the magnitude is just a distance between points. So of course it would make sense that the distance between those 2 points would be the distance formula, and that's exactly what that comes from. So also I'd like to point out that notice the notation here. Remember that the absolute value bars around a vector symbol is indicating magnitude or distance. An absolute value back in the day in two-dimensional representations was a type of distance. It was reflected in that, in fact. So let's do a little example with this. Here we are. And here's our little example. You don't have to write down all these words, but we do have to write the ordered pair that represents the vector from x to y. Then find the magnitude of xy. And actually, I should put the little harpoon symbol on that. There we go. Bam. Thing of beauty. So, if I want to find vector xy, that is going to be the little angled bracket, guys, of, and I'm going to take, let's see, if it's ending at y, I'll do this y, x coordinate, subtract the -3, comma, -2 minus 5. That was one too many commas there. So the vector written as an ordered pair, 4 minus a -3 is +3, which is 7. -2 minus 5 is -7. So here's my vector xy. All right. So this vector is the same direction and magnitude as the line drawn from this point to that point. Even though it is no longer kind of located at those points, it's like I've shifted it so it starts now at the origin. So the vector that I'm actually talking about would be this vector where, right, it starts here and then over 7, down 7. This is the vector that I'm talking about. All right, and in fact, we could even refer to the fact that its horizontal component is 7 and its vertical component is -7, right, so to speak. So that would be the vector I'm describing. And if I shifted it back around to starting at -3, 5, it'd still have the same magnitude and direction. So now it says find the magnitude of xy. Well, the magnitude, we could use the little formula. So many symbols for this. Yeah, it's kind of a sad y. Now, it's just going to be y2 or x2 minus x1, right? So that's going to be the 4 minus the -3 all squared, plus the y2 minus y1, so that's -2 minus 5 all squared. And you might realize, wait a minute, didn't I just do these subtractions? And yeah, we did it right there. So you could have just skipped and just squared those and added them together. So let's see, this is going to be the square root of 49 plus 49, which is, I believe, the square root of 98. Which, of course, you guys would not leave it that way. you'd be like, that's the same as the square root of 49 times 2, friend. Or square root of 2. So that is going to be 7 rad 2. Would be the magnitude of the vector, which also it makes sense, notice, because this is a 45, 45, 90 right triangle. And if the two legs are 7s, then this would be the square root of 2 times longer than that.
Do these brackets, these ones here,
Yep.
have to be angled like that?
Yes, they do.
Why?
Because they represent a vector starting at the origin. So if I just talked about 7 comma negative 7 in parentheses, that would be referring to a single point there, which does happen to be the terminal point of that vector, but it is not referring to the entire vector. Okay? So with those little angled brackets, it's describing the purple vector here is what's going on. So there is a benefit to writing vectors in this format, and that is when I do operations with them, we can actually do a whole bunch of easier math as a result. It's quite nice. Quite nice. It says the following are defined for vectors A, right, A1, A2, and vector B, B1, B2, for any real number k. All right. So if I add vectors A and B, notice what occurs. I merely add their x coordinates and their y coordinates, and I make the new vector. Bam, bam. That's it. Super easy. You could almost think about that similar to like adding matrices. You remember that back in the day? When you'd add two matrices of the same size, because that was the only size matrices you could add, you would, in fact, add their corresponding elements. I don't know if I can appropriately refer to these as elements, but that's what's up. To subtract two vectors, you subtract their corresponding elements. So subtract the x's, subtract the y's. That will give you your new x and new y for your terminal point. And then scalar multiplication, if I'm multiplying a vector by a number, it's somewhat of a distributive property in nature. So let's do some examples. Let's say, let's define some vectors first. Let's say I've got like vector A here is this guy, 2, -1. Man, by the end of this lesson, hopefully my angled brackets will look better. Because, yeah, sometimes that will look like a greater than sign, which then evolves into a 7, and then the 7 with a line in it. It's like the evolution of symbols there. Blah, 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 blah. Right? It's pretty great. So, so there's vector A. Let's say here's vector B, because I said so. So vector B is going to be like 3 and 8. How about? So if I want to calculate vector A plus vector B, I would just simply do 2 plus 3 and -1 plus 8. And I would get 5, 7. New vector. There's no triangle method, no parallelogram method. It's all algebraic. Yeah, like I said, I think so far this is pretty easy, right? Would we agree? Like, it's not too crazy. All right, let's make it crazy. What about vector A minus vector B? What? Mr. Waddy, you're crazy.
Yeah, you're crazy.
Yeah, tú estoy loco. Is that, no, that was wrong. Tú estás loco?
Are you saying to me that I'm crazy?
I don't know. A crazy person can't speak Spanish, right? I don't know.
I'm only irrational people.
So let's see. Whatever. Anyways, I'm sure no, Khan Academy can't help you with your Spanish either. Check out Google Translate. So, so yeah, we would just subtract their corresponding elements. Bam, there's a new vector. Good stuff. All right, what if I wanted to know what is -3 times A? Well, multiplying by a scalar, all I done do is multiply each component by the -3. That 2 looks like a Z. So that's -6. No. When I write a real Z, my Z's got the lines through it. Which maybe is the part that evolves after the 7. It like gains another limb. Becomes more efficient. With all these limbs it can like climb. finds an appropriate habitat. Who knows? Okay, well, how about this question? Last one regarding these. What if I have negative a plus 2 times b? So let's see, negative vector a would just be the opposite of those, so negative 2, positive 1. Right? Plus 2 times vector b would be twice these values. Right? And now I would just add those together.
Wait, shouldn't it be twice 8?
Oh! 8's not the twice of itself? My bad, I didn't realize. Negative 2 plus 6 is 4, and 16 and 1 is 17. Right? So that's not that bad. No es más mal. So, let's do an example where things get a little bit more interessante. So, I'm going to scroll on over here.
You should never use 7 next to these brackets.
Let's see. I'm not going to make you guys write this down. I do want you to draw a picture.
Oh.
So, radiology technicians Mary Jones and Joseph Rodriguez are moving a patient on an MRI machine cot. Okay. Ms. Jones is pushing the cot with a force of 120 newtons.
That's 1 kilogram times meter per second squared.
Wow. Thank you, Mr. Durant.
What?
Number 35. Wow. I like it. So, I'm going to draw a picture representing that. Now, let's assume, maybe I'll draw a little cot. I don't know what these cots look like. Here's my little bed thing, and it's going to have like the cool crisscross bars and the wheels on it. Who knows? I don't know. I am. You don't have to draw the cot. So here's my awesome cot, right? Bam. So she is pushing the cot with a vector force. So I'll say she's pushing it from the back at 55 degrees from the horizontal
Yeah.
and 120 newtons. Yeah, she is a little bit. I mean, she's pushing horizontally and down on it if we think about the vertical and horizontal components of it. If you want to break it up like that, which we will, my friend. And how about this Mr. Rodriguez is pulling the cot with a force of 200 newtons. Let's see, 200 Newton vector should be longer technically, shouldn't it? Yeah. At 40 degrees. Okay? Now, I drew those kind of tip to tail because they're representing, right, 2 vectors that are simultaneously exerting a force on this cot. So it says, what is the magnitude of the force? What's the resultant vector is kind of what we're talking about here, right? So what I'm looking for is the cot is actually experiencing some motion somewhat like this. Right, that's the resultant that we've got going on. Right, so that's what I'm looking for. What is the overall force being exerted on the cot? Right? One person's kind of pushing from the back, one's pulling from the front, but they're not doing it at horizontal angles completely. Right? So, so let's represent these vectors, if we shall, as vertical and horizontal components, because then I can write those as ordered pairs. Okay, is the idea. And then once they're ordered pairs, I can find their sum rather easily. So let's call the green vector, what's that, Mary? So we'll call that vector M. And we'll call the other vector, what's it, Joseph. So we'll call that vector J. All right. So I'm going to want, let's think about this green vector here. This is maybe a little bit better as 120 newtons there, right? And I'm going to want to figure out what the vertical and horizontal components are. So I'll call this vector M sub X, and this is vector M sub Y. And let's see, this angle was 55 degrees. Right? So let's find vector m sub x. All right, so to do that, well, think about it from this angle's perspective. That is the adjacent, and the 120 is the hypotenuse. So the trigonometric ratio that compares adjacent with hypotenuse is?
Sine. Cosine.
Cosine is what I heard, yep. 55 degrees is equal to adjacent, so that's the magnitude of mx over 120 newtons. Right, so that means the magnitude of mx is just going to be 120 times cosine 55. Is that right? I believe so. And I believe that's about 68.8292, at least according to my hand trick that I just did. Let's verify this. I did these calculations earlier. I want to make sure I'm at least right on it a little bit. Yeah, we're good. So that's the horizontal component. How would I find the vertical component? Well, yeah, it's the opposite compared to the hypotenuse. I could use sine, right? Technically, between this and this, I could Pythag it if I wanted, because that's a right angle. But let's just use sine. So sine of 55 degrees is equal to the magnitude of the, what was her name? Mary? I don't remember anymore. Sure. So the vertical component's magnitude would be 120 times sine of 55 degrees, which is 98.298. Is that magnitude. Oh, I left this gross circle there. I can't get rid of that effectively. Whoop. That's good enough. There. Bam. So, so that means that the Mary vector, is her name Mary? Am I being disrespectful? Is Mary Jones. Mary Jones, her vector is the following. So I could write this as 68.8292, comma 98.2982. Right? So there's Mary vector. I just realized these people are named like Mary and Joseph. It's a little religious, I think, for this vector problem. Maybe. I don't know. I got this from the book. Not the Bible, but from like the math book. I didn't make this problem up. So Joseph, he's pulling on this cart 200 newtons this way. Let's just draw the triangle. I might shortcut some of the trig for us. So 200 newtons, right? And then I'd want to break that down into the horizontal and vertical components. Right, so this will be vector j sub x, and this would be vector j sub y. And so to set that up, you would do some trig again. And oh yeah, what's the angle? 40 degrees. So to find jx, it's going to be cosine of 40 degrees equals j sub x over 200, right? And then I'd get 200 times cosine 40 is j sub x, right? Right. So the magnitude of jx is equal to, when you do the 200 times cosine of 40 degrees, I believe I get 153.2089 right there. And if you end up setting up the sine, 200 times the sine of 40 degrees for the magnitude of jy, we end up getting 128. That's an ugly 8. 0.5575. Right, so I find those two things. Right. Let's see, how much? Man, you know what's crazy? Joseph is pulling more vertically and horizontally than Mary was pushing all together. Jeez. Joseph. Who you trying to impress, Joseph? Jeez. Okay, maybe. That's an MRI.
That's true. I don't think there's, emergency MRI, that would be.
Nah, that's probably a thing. Yeah, I'm sure. So the Joseph vector would be 153.2089, comma 128.5575. So if I want to find the sum of these two vectors, what do you think I would do?
Add the x's and add the y's.
Add the x's and the y's. So ready? The Mary plus the Joseph vector, also known as the Jesus vector, maybe? I would just add their corresponding elements. So 153 plus 68 is 222.0381. I'm going out to 4 decimals here. I'm an overachiever. And 128 plus the 98, I get 226.8557. So that's that vector. Okay, that's the resultant force, or, well, the resultant vector. Yeah, which is a force, I guess, because of magnitude and direction. So that's that vector right there, okay? Now, I want to find the magnitude of that vector. We had that little formula from a moment ago, and that formula is just merely the distance formula. So if I want to find the magnitude of Mary plus Joseph together, square root of 222.0381. I would square that, add that to this guy squared, right? And I would just distance formula it. I'm just using these right off the bat because I already did the work of like adding those together. So equals, all right, and you get the square root of 100,764.4265. You can skip right to the end here if you want. And you end up getting 317.4341 newtons. All right. So that's the amount of overall force being exerted on that cart. Now, that doesn't mean that's at a horizontal angle. Okay, in fact, I'm quite certain it's not. But we could actually end up going back and doing some trig later on, which I think we'll talk about later as to how to find this angle here right there to figure out what that is. But let me point out one last concept, which is called a unit vector. Unit vectors. Now, when we talked about unit circles, what did that mean, or a unit circle? Yeah. Radius was 1, so unit vector has a magnitude of 1. And the horizontal unit vector is often referred to as I. The vertical unit vector is referred to as J. They should have realized I was already used for imaginary numbers there. But what you can do with these as the sum of unit vectors. It's just a different notation, really. So if I had the vector, say, 2 comma negative 1, I could write that as 2i, 2 of the i's minus 1 of the j's.
Wait, and I is.
Where I is the horizontal, right? So hence the horizontal, J is the vertical.
But why would you ever use that?
It's just a different notation, so I just want to make sure you're ready to see it that way is all. So anyways, thanks for watching, friends.
Every single one.
Have a great day. Bye-bye.